Good morning, good afternoon, or good evening. We are now on to question 7 of the 2024 Step 3 paper. As with all these questions, please do have a strong go at them yourself before you watch this video and get all the spoilers. As soon as you do spoil one of these, you lose a lot of the value of attempting it yourself. Question 7 then. Here we are not needing to worry about convergence. Luckily, convergence is a very complex issue, normally held back for a first course at university. So we don't need to worry about convergence here. We're just going to put some bounds and such on these sequences. Things to notice that the Fn and Gn sequence do look incredibly similar. Just the Gn sequence has alternating signs, whereas the Fn is all additions. That may come to be relevant in some way later in the question. So part A of the question, by considering a geometric series, we want to show some bounds on F. Well, first I'm going to do the easy bit. First observe Fn is a sum of positive terms, which is going to mean that Fn is greater than 0, n being a positive integer here, so that's all good. Also, let's now do what it suggested. Let's compare Fn with a geometric series. So Fn, we can say, is going to be less than, well, the first term I'm going to leave alone, but the next term I can make slightly bigger by making the denominator smaller. So the second term I'm going to have an n plus 1 in the denominator. The third term I'm going to be even more aggressive and I'm going to make everything into an n plus 1. So in each of these terms I'm making the denominator smaller, so I'm making the sum bigger. So therefore this sum is bigger than what we originally started with, but this thing, which is a geometric with, apologies, the pen isn't doing what it's supposed to do, with A is 1 over n plus 1, which is also R, and we're doing the infinite sum, which is going to therefore mean that Fn is less than A over 1 minus R for the infinite sum of that series. Multiplying top and bottom to clear the fractions, we get as so this is just 1 over n. So thus 0 bounds below and 1 over n bounds above of this Fn thing. So Fn is always going to be some decimal value. Fn itself can never be an integer. Part 2 is going to be very similar. By comparing consecutive terms, and to me that's actually incredibly scary because convergence is an issue when you come to think about these things. We've been told not to worry about convergence, so we'll get away with it. So comparing consecutive terms, so I'm going to say that Gn, which at the moment is 1 over minus the next term plus the next term, and I do want to write one more even though these terms are becoming incredibly long, because if I'm comparing consecutive terms I want to have at least 2 of them, 2 pairs of 2 to worry about. Plus dot dot dot. So by what it's suggesting, I'm going to smash the consecutive terms together. So if I take those first 2 terms, I need to have a common denominator of n plus 1, n plus 2. So I times top and bottom of the first one by n plus 2. I'm subtracting 1, so that's just n plus 1 on the numerator, which I'll clean up in a moment. The second one, I need times top and bottom of the first by n plus 4. So that's going to be n plus 3 on the numerator with all of that junk on the denominator. And we can then imagine that the next term, if I did want to continue the pattern, will be an n plus 5 over all of that junk up to n plus 6 when I combine those together. So I've kind of spotted the pattern to see what's going on, and now something cancels, which I don't know whether I like them cancelling, because it's kind of taking out quite an obscure term, but I'm going to do it anyway. So this is going to be 1 over n plus 2. Now this term is 1 over n plus 1, n plus 2, n plus 4. And the next one, don't really want to write it all out, but I've already started now. That one's missing the n plus 5 term. Okay, so one thing we can say, which is a sum of positive terms, which is going to mean that Gn is indeed greater than 0. But now we want to show that Gn is less than 1 over n plus 1. And it's not quite as clear cut. It would be quite nice to have this as a geometric series and get a calculation such as that, where the A is and the R is. The issue is these terms here, this 1 over n plus 1 term, is a little bit awkward because it's not, we can't put the same bound on like we did up here. We can only make the denominators smaller to make the, make the denominator smaller to make the whole fraction bigger. Well, we can't make that denominator smaller to turn it into an n plus 2. Now, if we could argue that these together work, then I can get away with it. So maybe we can, if we can show, and again I'm going to do, this will be the scribbles that you do on your scrap piece of paper elsewhere. I know what I'm aiming for, now I just want to show. So if I can show that n plus 1 and n plus 4, now which way round do I want this to be, to n plus 2 squared? I want to make the denominator smaller, so I want to show that. And if I do expand these out, this is plus 5n plus 4, and this is n squared plus 4n plus 4, which is indeed true. So I'm going to say, notice that n plus 1, n plus 4, which is equal to n squared plus 5n plus 4, is bigger than n squared plus 4n plus 4, which is n plus 2 squared. Oh, I'm a little worried again because this is now too many. The denominators, there's too much in the denominator. My r, I'm multiplying by 2 copies, not just 1 copy each time. So maybe I didn't need to bound so aggressively. Yeah, maybe I didn't need to worry about this quite so much. But let's follow it through and we'll make another inequality in a moment. So that's going to mean that this g of n is going to be less than, so I'm making the denominators, no, I'm making the denominators smaller. So that's not what I want at all. This isn't the right way round whatsoever. I made the denominator smaller in changing. I wanted to make the denominators bigger. But I can still say that g of n is going to be less than, well, what if I just get rid of all the n plus 1s? If I just get rid of them, then I'm certainly making the denominators smaller, so the whole thing has become bigger. So this is certainly less than 1 over n plus 2 plus 1 over n plus 2 n plus 4. And why stop there? Let's be even more aggressive with the way we're bounding. Let's get rid of even more factors. So I'm going to get rid of the n plus 3 factor in that term. And then the next term, I'll get rid of the n plus 1, the n plus 3, and the n plus 5. So now this is less than 1 over n plus 2 plus 1 over n plus 2 squared. This is now the same trick. We're making the denominators smaller again. So actually this is a very heavy-handed bounding we're doing. So that means this 1 over n plus 1 bound that we're eventually going to get is going to be quite a weak bound. And this is equal to a over 1 minus r, which is, after simplifying through, exactly what we wanted. Thus 0 bounds below, and 1 over n plus 1 bounds the gn above. Okay, so we've shown some bounds on both gn and fn. We haven't really got to the point of the question yet. So far we're just manipulating series and inequalities. Part 3. Show that for positive integer n, 2n factorial e minus f of 2n and something else are both integers. Okay. Well, this means we need to remember, or at least go and find, what e is. So we should probably first recall that e is 1 plus 1 plus a half plus a third, etc., which we can write as the sum from n equals 1 to, or n equals 0 to infinity of 1 over, and this is a 3 factorial, these are all factorials, 1 over n factorial, which is kind of a little bit like what we're doing, because we have these almost factorial-esque sequences, but starting on the top end rather than starting at 1, 2 factorial, 3 factorial, 4 factorial. We started at the top rather than at the bottom. And I really should use a different letter here because I'm going to use that n later on. So I'm going to sum over m in this. So I want to show that. So then let's consider 2n factorial e minus f of 2n. Okay, well, this is equal to the sum from m equals 0 to infinity of 2n factorial over m factorial minus, that was a bad summation symbol, minus the sum. Now f is a little bit awkward, but I am going to try and write it using factorials. So this is the sum from, let's say, k equals 1 to infinity. That first term kind of looks like, I kind of want to think of that first term as n plus 1 factorial on the denominator and n factorial on the numerator. So maybe I do want to sum from k equals 0, because then I can call this thing n minus k factorial. So that's when n was 0. The second term looks like n plus 2 factorial. And I've cancelled out again. Actually, I've just cancelled out n factorial again, haven't I? So on the numerator, I can always have just n factorial. And of course, I'm going to put the 2n in that spot later, but I want to write the f first. And then my next term, my next term is then just n. Oh, I'm still on the eraser. N factorial, n plus 3 factorial. Okay, so I do want to sum, I think, from k is 1. And this is going to be n factorial over, or 2n factorial over 2n plus k factorial. Does that look right? Well, when k is 1, I am getting this term, again with the 2 n's in the places of the n's. When k is 2, I am getting this term, which does match with what the f is. So that looks about right. Now, did writing it like this help? That's a really good question. We want to show that this is an integer. So really what we need to show is that when m is bigger than 2n, everything is cancelling out. Because when m is smaller, this thing here is just an integer. So really what I'm thinking is this first section here is some infinite sum starting with m is 0. And then this thing is some infinite sum that's going to cancel all of this out perfectly. Now the difficulty is, and the thing which I'm not liking right now, is this only has odd. Oh no, it doesn't. It does have odd, even, odd, even. It just kind of looks like an odd number. So this first sum is a sum starting from 0, whereas the other one looks identical, but it's starting at 2n plus 1. Well, if I subtract off the sum from 2n plus 1, I'm left behind exactly with the finite sum here. So actually these two sums are summing the same thing, just in a slightly silly way. So I can write this as the sum from m equals 0 to infinity over m factorial minus the sum, and I'm going to write this one in a silly way. I'm going to start at 2n plus 1 to infinity by just relabeling that denominator. And now it's more obvious. When I subtract these sums, I'm just losing all of the later terms. This is the sum from m equals 0 up to 2n over m factorial. And now this is going to cancel out. Every single one of these cancels nicely. So this is really 2n factorial plus, I think I want to do this bit in words rather than in algebra, because I'm kind of losing things on the end of the sequence, plus 2n factorial. Sorry, I think I want to write this as 2n minus 1 down to 2 plus 2n minus 1 down to 3, all the way down to just the last couple of terms will be 2n and then plus 1 as the final term. And this is just the sum of integers, which is an integer. Okay, so seems a little odd there. But the idea, I think, is the fact that E, the first term, is this infinite sum. The F is this infinite sum. So if I subtract them, I'm left behind a finite little bit of this sum. Okay, proceeding to the second part of this question, we now have 2n factorial over E. So then also, and I'm expecting this to do a very similar thing. So now we've got 2n factorial. I'm just going to write this as e to the minus 1, because we know that that has a very similar summation. And now I'm doing g of 2n. So this is going to be the sum from m equals 0 to infinity of 2n factorial. There's going to be -1 to a power. Is it just the power m? I'm going to check that I've got the signs the right way around on that in a moment. When m is 0, I do want the first term to be positive, and then it swaps to negative, positive, negative. So that does indeed work. Minus the sum from k equals 1 to infinity. Now, how am I going to write g? Well, again, it's going to have a -1 to a power. I think I want to start summing at 0, so I can just have this power to be k. So the first term is positive. The first term looks like the n factorial. And actually, every term's the same, so I don't even need to worry about doing anything silly. I can just steal what I decided for the f above, but now with an extra power. So this is going to be the sum from m equals 0 to infinity of its thing. And now I'd quite like to show that this second summation is the sum from a different starting value. And actually, because I changed this, I do want to keep this the same bound as my k. So I'm going to change this up here to k plus 1. Because otherwise I need to change what's in here, and I'm not going to enjoy doing that as much. So the starting value is now 2n plus 1. So I've got m factorial on the denominator. I've got 2n factorial on the numerator. And this is where my -1 is going to have a different power potentially. So when k is 1, m is... so yeah, when k is 1, k equals 1 corresponds to m being 2n plus 1. So so m is 2n plus k. So I'm doing this way more awkwardly than I have to. So this new power is going to be really awkward. So -1 to the k plus 1 is the same as -1 to the m minus 2n plus 1. And I've just spotted this. Yeah, there's a sign error which I made here. This is a plus in between here, which is actually going to make everything a lot more pleasant. So this is equal to -1 to the power of m plus 1, because this even little bit here, an even power, doesn't impact the powers of -1, the power of m plus 1. And this is where that sign error that I just spotted is going to help out. We've got this extra plus 1 here. So this is going to equal, that plus 1 can be used to change this into a minus. So we do have the same concept going again. This is now going to be the sum from m equals 0 to infinity, not to infinity, up to 2n of this thing over m factorial, which is 2n factorial minus the next term plus, sorry, that term is going to terminate at a different point, down to 2 plus, etc. And eventually we'll get down to the end. The very last term will be a plus 1, so the term before is a minus 2n plus 1, which is an integer. Okay, so we've used the same idea twice, that these infinite sums, we're kind of cutting them off after some point. So how does that do anything useful? So now we're on to part 4 of the question. So part 4 is saying let QE equal P over E for P and Q are integers or natural numbers. Then that is an integer for all values, for all positive values of n. Okay, so it looks like I'm trying to do something with the expressions I've got above. If I multiply this one by Q and this one by P, then what does that say? So let's just do it and actually manipulate afterwards. So part 3 implies that Q times 2n factorial E minus Q f of 2n and P times 2n factorial over E, because that's what our result for G was, plus P G2n are integers. And now if I subtract these, and I actually want to subtract these in the wrong order, so subtracting reverse order, if I subtract these, I'm going to get a 2n factorial lots of P over E minus QE and plus PG2n plus QF2n is an integer. We start with 2 integers. If we subtract them, we still get an integer. But that first term, this thing here, is 0 because of that assumption we've made. So PG2n plus QF2n is an integer. You should start to feel quite worried. If you are keeping track of what's going on in the question, we have the f of n is a really small decimal, g of n is a really small decimal, but now we've got multiplying them and adding them together is going to be an integer. And actually, if we do look ahead, we're trying to show something's irrational, so we are looking for a kind of contradiction. So let's put everything we have together. So let's assume for contradiction that e squared is rational. Say e squared equals p over q for p over q integers, positive integers. We know they can both be positive because e squared itself is going to be positive. Well, that means by rearranging this, multiply up by the q. Sorry, the pen isn't doing quite what it should. Is that, which then part 4 means that pg2n plus qf2n is an integer for all n's. That's exactly what part 4 gave us. But, well, let's pick a particular value of n and show that this thing can never be an integer. So, but pick, well, I'm going to pick n to be, I'm going to pick n to be p, which we know has to be greater than q as e squared is greater than 1. So we know the numerator of this e squared has to be bigger than 1. Sorry, it's bigger than the denominator. Then we know that 0 is smaller than pg2n 2p now plus qf 2p. And I basically want to show that this expression has to be less than 1, so we have an integer that's less than 1, which is of course impossible. So this is less than p over 2p plus 1. This is by part 2 of the question and part 1 of the question. So part 2 gives me my bound on g plus q over 2p plus 1. Sorry, just over 2p. So then if I want to make this bigger, I can say this is p 2p plus 1 because p is bigger than q. I can say as so. Now if I want to make this bigger again, I can make the numerators smaller. So this is p over 2p. This fraction is slightly less than a half, but I'm saying it's going to be, I'm bounding it by a half, which is equal to a half plus a half, which equals 1, i.e. pg 2p plus q f of 2p is an integer strictly between 0 and 1. Well, if you can tell me an integer between 0 and 1, I'll be slightly worried. That's a contradiction. Thus, e squared, which was the assumption we made at the beginning, followed only logical steps and got to a contradiction. Thus, e squared is irrational. A really nice proof actually for e squared being irrational. And if you are interested, I would recommend you go and look at the proof for e itself being irrational, and you'll notice it's a near identical trick. We use some functions to cut off the end of e so that it looks like an integer on multiplying by some sufficiently large n, and then showing, well, actually the cutoffs can't be an integer, so therefore we can never cut off an integer off of e, so e is always going to have non-integer parts no matter what we multiply it by. I really enjoyed that question, quite a clean question. A lot of manipulation of inequalities. I think I've said this in some of the step 2 questions. Manipulating inequalities is not a skill used very much at A level, but is an exceptionally powerful skill at higher levels, at university levels. So they often put those kind of skills into the step questions to see if you can start thinking in that way. Otherwise, the rest of the questions will be in this playlist, and good luck.